We'll move now to the Q&A session. So we've heard 3 papers. They're all online. You can read them. And let's start with a question to Ravid. So Ravid, to remind the audience, you showed a comparison between several architectures for deep learning for tabular data and gradient boosting trees, but you then showed that an ensemble of all of them is better than each one of them, right? So can you explain, like, why do you think we need all of them, including the trees? Why do you really need all of these models together? Why do they have incremental value on top of each other?
I can try, yeah. So I think that that here in these models, they represent they are very different from each other. Their structure is very different. It's not like in vision that you're most of the time taking similar models with similar structure that probably will represent your data similar, and their predictions will be similar to each other. Here, they are really different, all these models, so their prediction, they probably are very different, and they are they have good answers, or the correct answers for different examples. So there is advantage to take them and to make an ensemble of them, all of them together, because you have an advantage to be correct on different types of examples.
Cool, thank you. And another follow-up question on that, I saw in the chat a few people asking about that. So do you think that there are types of data that are better for deep learning and types of data that are better for tree-based models? Maybe it's the amount of categorical versus numeric features in the data or something like that?
Yeah, so this is a very good question. Probably the answer is yes. And one of the problems when we are talking about tabular data, that it's very there are a lot of different problems with a lot of different features and representations, and you have here some mix that it's very difficult to understand what are the important features in your data sets. And yes, probably the different models are working better for different types of tabular data. But the answer is that at the end, I don't know. Like, we need to, of course, that one of the questions that we want to check is exactly this. Can we characterize what are the features in the data sets that gives you better results?
Thank you, Ravid. Zohar, over to you. So to remind the audience, you presented Tab Transformer, which is a deep learning architecture to create embeddings for categorical variables. So you showed that you do not beat XGBoost for supervised task, but for a semi-supervised task that was different. Can you elaborate a bit on that? Why do you think that there is a difference there?
Good question. So I think, well, at the end of the day, it's a different method for semi-supervised, right? We didn't just beat XGBoost or like it was with a semi-supervised method, but I'm not sure exactly why that is. They're very different methods, the semi-supervised technique that we use. Yeah.
Okay, cool. And another thing, so you provided, you talked about an implementation of your method. So do you have any practical tips for people that are going to use this implementation in their use cases, like where to use it, when, how?
Yeah, I think semi-supervised is kind of the most natural place, and moreover, if you have one big data set and a lot of small tasks, which I guess happened to be the case for me, that's kind of great because you need to pre-train only once and then fine-tune on the smaller tasks. That's kind of one kind of, perfect fit use case for it. I'd say for people wanting to do research, when you have very little amount of labeled data, there's a little more I think you should do for the pre-training procedure, because the top wasn't really affected by unlabeled data, and then we stopped the experiments.
Thanks. And another question. So how would you use this method together with different types of data, for example, with textual data or with images?
Well, right now, this is a component for the categorical. So I'd say, if you have text, use your favorite text embedding, like, BERT, uncased, whatever. And that's another embedding of the text component, then plug it all together. You can have variations of it, but I'd start there.
Thanks, Zohar. Giora, so thank you very much for your interesting talk. I will remind the audience that you described a method that you took some idea from statistics about linear mixed models, and you applied it to create better embeddings of high cardinality categorical features, which are like, for example, huge cardinalities like user IDs. So you described that you have a dedicated loss function, right, to take this into account. Could you give us a bit of intuition? What is in this loss that is taking the high cardinality features and like treat them better than do nothing with them?
Okay, so I can't go back to the specific formula, but if you look at it again, you might recognize that in this specific case of a regression setting, it's very similar to mean squared error, but it is weighted. It's weighted by a very specific covariance structure. That's the secret ingredient of everything that we're doing. We specify a very specific covariance structure which makes sense in the context of our features. Like in the context of a categorical feature, there is a specific covariance structure that makes sense. And in the context of a spatial feature, it might be like an RBF kernel or what people might know as a Gaussian process. So for the general audience, I would say think about mean squared error, but weighted. Yeah, that's it.
Thanks. Another question regarding your talk is isn't this random effect approach just another form of network regularization?
Okay, so in the case of a single categorical feature, linear mixed model with a single variance term is very similar to regularized linear regression or ridge regression. We can show mathematically it is borderline equivalent, but this is where it stops. Once the covariance structure is slightly more complex, like an RBF kernel, which we just discussed, this is considerably different than just regularization. We are fitting a very specific covariance structure to data in a way which scales.
Thank you so much. So I want to give each of the presenters maybe less than a minute, maybe 30 seconds to maybe give us their finest thought about what do you expect from the future of deep learning for tabular data? So Ravid, let's start with you.
Okay, I think so probably the future will be involved more transfer learning, for example. We saw that in other fields. We see that transfer learning can make huge impact, and all these pre-learned models can make make a huge impact on other tasks. So yeah, I hope that that we can figure it out how to make these transfer learning also for tabular data, and how can we use this huge amount of data and to transfer the knowledge from one task to the other.
Thanks, Ravid. Zohar, do you have your 30 seconds, sorry.
Yeah, I can't go for 30 minutes, but yeah, I mean, transfer learning definitely, plus one on that. I think another big thing to tackle is the relational databases. Because like in practice, you rarely have one table, right? You have a bunch of tables, you need to join, you need to aggregate, and right now it's kind of black magic, this how do I aggregate things? It's kind of an art, and being, more principled around that, I think it would be, a big step.
Yeah, I agree. Thanks, Zohar. Giora, what's your shot?
I would like to say that it's also my experience. I was surprised by Ravid's result. It is also my experience that currently off-the-shelf methods like XGBoost are like the king of tabular when it comes to tabular data. But I have faith in deep learning, and I think it won't be for long, because I think that that's exactly what we're working on right now, taking all that we know from working with tabular data and applying it somehow in a way which scales into deep learning.